Okay, hello everybody. Can you hear me at the back? I hope that's coming up good. Right, so I've got about 45, 50 minutes to try and tell you why my research is so exciting. It's going to focus on dark matter, which maybe some of you have heard of, but I will explain what that is. And I'm going to try and explain what I've been doing to try and see this invisible, ghostly puzzle, this last part of the universe that we don't understand. But before I do want to try and add a little bit about who I am. I'm not just a professor, there's a lot of other things going on in my life. So I grew up in South London in a little place called Croydon, which I believe is a bit more famous these days. And then I went off, as I said, to Royal Holloway to study physics, and decided that I didn't want to become an accountant. I actually wanted to do some really fun physics. There I found a cat underneath the department, and so I have a cat. And then I went to Sussex to do a postdoc in very similar work to what I'm doing now, where then suddenly I got a first dog, second dog, had a child, came over here, had another child, and then stayed here at Cambridge, hopefully permanently. They're not just little anymore. I used to have photos of babies up here, and they're getting bigger and bigger. I'm hoping the future is going to be just as busy and exciting as all of this. I'm hoping actually there's going to be a new discovery related hopefully to something that I'm doing in research here, but maybe it won't be me, maybe it will be one of you that are sitting here in this room. So let me try and tell you about that. So I'm going to tell you about particle physics, and I know there's some people in this room who know about particle physics, and there's some people that might know absolutely nothing about particle physics. And I'll try and break it down for you. Particle physics is the study of the most fundamental blocks of our universe, things that we don't think can be broken down any further. So we've got fundamental particles that make up the matter in the universe, and then we've got fundamental particles that govern the forces between them. So on the outside here, I don't know if this is going to show up. No. On the outside here, you've got 12 matter particles. The ones on the top here are called quarks, and they come with fantastic names like up, down, charm, strange, and top and bottom. There's 6 of them. And the up and the down quark are the ones that make up protons and neutrons that you might have heard of in the center of atoms. We've also got another 6 of these things. Some of them you might have heard of, the electron. We've also got the muon and the tau, which are like heavier versions of the electron. And then we've got 3 ghostly particles called neutrinos there. So along with the up and the down quark, the electron makes up that last bit of an atom circulating around the protons and neutrons. So the building blocks of the basic universe are actually just up quarks, down quarks, and electrons. And that's pretty much all we need to know. But what we find is when we go up to higher energies, actually there's more massive exotic versions of these particles that are unstable, that eventually decay down to those sort of up, down, and electrons there. Now there are, depends on how you see it, 4 fundamental forces that we know about in our universe. The first is gravity, and I'm going to say absolutely nothing about gravity here. It's absolutely weak at the tiny length scales and mass scales that we're looking at here. The other ones you might have heard of, the electromagnetic force and the photon. That is the force that governs charged particles, so it's all to do with electric charge. There's another one called the weak force that's responsible for radioactive decay. You might have heard of that. And there's particles associated with those W and Z bosons there. And then there's the strong force, which you may or may not have heard of. That's the force that holds quarks together, the up and the down quarks together to form protons and neutrons. And that's governed by the gluon. They're up there literally gluing them together, and it is a very, very, very strong force. It's well named. So we've got these 3 fundamental forces that we can describe with these 12 matter particles, and the new kid on the block here at the center is the Higgs boson that we discovered about 12 years ago at the LHC. That's the particle that comes about from the mechanism that gives some of these particles mass. So now we think we know where mass comes from. And it's this really nice, neat graphic of particles and the forces that govern them. And it seems really straightforward. but it's not really, and I'll try and explain some of the problems that we have. So I can put our 12 matter particles, I can arrange them like this in pairs, like 3 pairs of quarks and 3 pairs of what we call the leptons, like the electrons and neutrinos. And they come in 3 pairs, each 3 generations. Why not 4? Why not 2? We have absolutely no idea why 3. There's no magical number about 3, I don't think. There's also some nice symmetry between these, but there's also some big differences. So the electron is incredibly light, the neutrino even lighter again, and the top quark is about the same mass as a gold nucleus or a gold atom. Absolutely huge. There are orders of magnitude differences in their masses. So we don't know about that huge asymmetry in the masses, why, for example, they would be so different there. There could be a clue, something, maybe some new pattern in nature that maybe quarks and leptons here maybe aren't fundamental. We think they're fundamental, but they're not made up of anything else, but maybe they could be. Because there's things like when you put 2 up quarks and a down quark together, it gives you +1 charge, which happens to be the negative of the electron. Well, why is it exactly +1? Why isn't it 0.9 of an electric charge? So there's some very strange things going on that might suggest that we don't understand this, or at least we can't explain why. For every one of these matter particles, there's an antimatter particle. You may have heard of the antimatter particle of the electron, the positron, for example. As far as we know, matter and antimatter should be treated almost the same, but ever so slightly differently by these fundamental forces, which explains why some matter is left over in the universe and didn't just annihilate back down to nothing. So it kind of explains why we're here. But we can't quite explain why so much of us is here. We didn't end up with less matter in the universe. We don't know where gravity is. I'm not going to go there at all today. And there's also a big question about something called dark matter that is completely excluded from this graphic here. So why do we study particle physics? Why is this so interesting? So here we have a picture of the evolution of the universe, all the way from the Big Bang, time equals 0, all the way to about almost 14 billion years later, where we are now. And where we are now, we have atoms, we have galaxies, we have all of these large thing formations. But when you go back and back and back throughout the universe, actually things weren't bound together. We had very high energies, we had high temperatures, and the universe looked and behaved very differently. The particles that were hanging around were different particles. We could make some of the very massive ones in just the normal everyday conditions of the early universe, like the top quarks would have been hanging around abundantly because there was plenty of energy to make them. So what we'd like to do is try and understand particle physics all the way back in time, to try and understand the evolution of our universe. The moment we're probing up to around 10 to the minus 10 seconds with our current experiments, we can actually reproduce the physics that was going on at about 10 to the minus 10 seconds after the Big Bang. I think that's absolutely extraordinary. And we'd like to try and push this further to try and understand the physics that was going on even sooner after the Big Bang. So by having a look at high energy particle interactions, we basically have a time machine back to the conditions of the early universe, which is really cool. And every time we go back and back at higher and higher energies, we discover something new about our universe. So some of the biggest questions we have are, what are we made from and how did we get here? Not maybe usually the biggest science questions that you hear about, maybe more philosophy, but what we're trying to understand is what is the universe made from. I'll show you at the moment. It's made from very little of the matter that we know of, atoms and all of the particles from the Standard Model. It's only a tiny, tiny bit of the universe. And then how did we get here? So in the very early universe, we should have had matter and antimatter created in equal amounts. Where's all the antimatter gone? Or what we label as antimatter? Why have we been left over with one rather than the other? And in fact, why have we got so much of it? So if there are these small differences between how matter and antimatter is treated by the forces, we expect a bit of imbalance, but actually we can't explain the amount of imbalance we have. We don't understand why we're here at all. There's also some other cool things. So this dark matter in the universe is my biggest problem that I'm trying to solve here. You can see actually a smoking gun of a dark matter in collision of cluster of galaxies here. What you've got here is a picture of one galaxy cluster here and one galaxy cluster here, and they have already collided and passed through each other. Okay, so they're going off in different directions now. The picture is taken using two different technologies. The X-rays are showing you where the matter that sort of we're made from now, that's emitting lots of photons, is. And as it's passed through, it's interacted with each other and it's slowed down, and you can see it there. But if we take the same picture using gravitational lensing, not to show us where the photons are coming from, but instead to show us where the most mass is, what we find is actually all of the mass is here in blue. It didn't interact as it passed through each other, and it just passed through without interaction, very, very coldly, and ignoring everything. So this is a smoking gun that there is dark matter in galaxies. So galaxies, dark matter was first actually observed, or the effects of dark matter were seen when we had a look at how galaxies rotate. So there was something quite surprising when it was measured how galaxies rotate. The speed of the rotation of a galaxy depends on how much mass is inside a galaxy. The faster it's spinning, the more mass there must be for it to be holding on and not flying off. So the speed of rotation is a bit like if you're sitting on a roundabout. If it's going even faster and even faster, you've got to hold on very, very tight, and that's the same as the gravitational force because of mass inside of the galaxy. So what we expected from the stars that we saw, from the amount of mass that we could see from light inside a galaxy, that it should have fallen off as you get further away from the luminous disk. But from the measurements that we have, it doesn't fall off. In fact, it just keeps increasing. So if all of these stars in this galaxy are going around that fast, there's got to be something holding them into the galaxy so that they're not flying apart. Okay, so there's more gravitational force there, which we believe is due to this dark matter that we cannot see. There's another way that we can sort of see the impact of dark matter as well, and that's in the cosmic microwave background radiation. If I take you back here, early in the universe, it suddenly became, we suddenly had some binding together of some of our particles into nuclei, into atoms, and suddenly the universe was completely transparent to photons. And we can actually see that sort of very ancient light from the early universe. We call it the cosmic microwave background radiation. Some of it is part of the sort of black and white snow when you turn on old televisions when they're not actually tuned into anything. And it's a fantastic source of information for us from the very early universe, and it's affected by the dark matter that was around in the universe back then. So when we look at that very ancient light, that cosmic microwave background radiation, we actually find at very large scales, so if you just sort of look at it across the sky, it looks absolutely isotropic and unchanging across the whole sky. Whatever direction you take it in, it looks exactly the same. But as you start to chop up the sort of blocks that you're looking at it over, you actually start to see a little bit more structure in the cosmic microwave background radiation. So if you go to smaller and smaller scales, as you have a look at this, there's no variation here, it's pretty much zero. But then the power spectrum here, the variation that we see on tiny scales really does change. And that changes depending on the nature of the universe at the time of the cosmic microwave background radiation transparency time. The first peak here actually tells you about the spatial parts of the universe, that it's flat. I won't go into that. The second peak here tells you how much baryonic matter is in the universe, how much protons and neutrons, matter that we know about from the Standard Model. That's only 5%. Only 5% of our universe is matter that we know about. Yikes. And then the third peak there tells us about dark matter. That 26% of our universe is dark matter. So 5 times the amount of the universe is dark matter. And the rest is something called dark energy, and that's responsible for the acceleration of the universe, but it's not a particle, so I won't go into it here. So what is this dark matter? What if it is a particle? What if it's a particle? Can we go back to our Standard Model particles and see what it could be? Well, these quarks, they're all charged. They should interact with photons. So it can't be them. I could see those with photons, hopefully. Also, the same reason it can't be these particles. They've got a charge. They should interact with photons. We'd be able to see it. So it's got to be hiding. It's got to be ghostly. It could be maybe these neutrinos. They are actually quite good candidates at first look. They're very ghostly, very weakly interacting particles, but they're also incredibly light. So to make up the amount of mass that we know dark matter actually makes up, we'd need so many neutrinos that they'd be streaming through this universe at such a high flux that they'd actually wipe out the structure of galaxies and our universe in general, like a great big tidal wave coming over it. So it can't be neutrinos. They don't fit the piece of the puzzle. Can't be photons, or we'd be able to see those. And then the gluon and WZ, they're not stable, so they wouldn't be hanging around after 14 billion years, and neither is the Higgs boson. So none of our Standard Model particles fit if dark matter is a particle. And that's really exciting. So if dark matter's a particle, it's got to be really stable. It's got to be heavy. It's got to be very, very weakly interacting. And there's nothing at the moment that's on the list that fits that bill. So what can we try and do? We can try and take our low energy universe today, and we can try and collide particles and recreate higher and higher energies of the early universe. And we've probed up to about 100 GeV, giga electron volts, in terms of energy. And we've discovered the Higgs up there as well. And we actually understand what we're seeing very well. We can make really accurate predictions. It's beautiful. Problem is that our theories are beautiful down at low energy, but we start to take them up to high energies and they start to break down, and everything, you start to get sort of probabilities greater than 1. That's just the start of the problems. So they don't extrapolate to very high energies, maybe to the energies of the very early universe, maybe where quantum gravity could be important as well. So we're limited though. When we build our colliders and we try and have high energy collisions, we're actually limited by practical things like space and technology. We can't keep building bigger and bigger. So how do we start to access this sort of desert in our knowledge between maybe these lovely mathematical theories where we have quantum gravity, but down to what we actually know experimentally? So what we're going to try and do is access this very high energy desert by making lots of precision measurements down here to see if we can see any deviations, for example. The analogy that I like to think about is, instead of opening the door and knowing what you've got and seeing what you've got for dinner, it's like smelling what you've got for dinner before you open the door. So that's what we're trying to do at the moment. It could be that there's some new physics very much up here that we can't actually access, but we might see some tiny effects of it down here. So there's 3 ways that we try and search for dark matter, 3 general ways. We call it shake it, bake it, or make it. So if you want to try and break it, we could look for very rare interactions. We know dark matter is in galaxies, right? We know it's there, or whatever we think is there. If it's a particle, it's there. And we might be able to detect some very, very rare interactions, maybe where a couple of them change into some Standard Model particles, maybe like photons or high energy electrons and positrons. So we could look for that, where it's basically broken itself, very rare things inside galaxies. Or we could build great big vats of liquid argon or xenon detectors under mountains and try and look for the very rare collision of dark matter with our current matter. And so if you think about our planet Earth and even just this area of the galaxy, we should be moving through a dark matter wind effectively as the Earth moves around the sun and the sun moves around the galaxy. So there's the direct detection where standard model particle and a dark matter particle could bang together, and you might be able to see the recoil of the standard model particle. But that takes too long. What I like to do is take our standard model particles, smash them together, and hopefully make some dark matter particles. And I use the Large Hadron Collider to do this, where we're taking protons at really high energy, smashing them together, and hopefully making something very rare and exciting like dark matter particles. So there's two main things that you need to think about with particle colliders. We're trying to produce something. Well, what do I know about dark matter? I know that we haven't found it yet. I would need to move everything up to higher energy, and maybe it's there. Maybe it's really massive and I need more energy to create it. So I'm going to put in more and more energy into my protons, and I'm going to smash them together at high and high enough energy, and that will hopefully give me my exciting, heavy dark matter particle. The other thing is that I know dark matter particles are incredibly ghostly by nature, really, really rare interactions at least, because we haven't seen them yet. So most of the time that we collide protons, it's actually boring stuff that happens. The protons actually can just bounce off of each other. That happens about 80% of the time. Then maybe a little bit more rarely, we could create a top and an anti-top quark. I mean, that's quite a newly discovered particle from 1995. That's very exciting in itself. There's still a lot of top physics to do, but that's not what I'm interested in. Or maybe 5% of the time we could get a couple of W bosons. Weak force is really interesting to study, absolutely. That needs to be done. But maybe a tiny, tiny, tiny fraction of the time we could have the energy and the possibility to create a couple of dark matter candidates. So what I want is a really high energy collider, high enough energy to create a couple of heavy particles, and I want the experiment to repeat at a very high rate. I want to smash them together at a very, very high rate to increase the possibility that I have some of these in my data set. High energy, high rates. So this is what we have with the Large Hadron Collider. I think it's absolutely fantastic, so I'll try not to wax on about this too much. But underground, just outside Geneva, we have about 100 meters underground, we have a tunnel with some shafts up there, where we have built an accelerator complex to accelerate protons to almost the speed of light and then smash them together. It's really, really cool. And around this ring, we've got 4 different points where we've dug out huge caverns and built huge detectors around the collision points to try and see what's going on. So we literally take protons from a bottle of hydrogen gas. It's as simple as that. It's not very fancy. We strip off the electrons off of the hydrogen, there's your proton, and then we send it around an accelerator complex of rings, getting up to higher and higher energy. So the source of it's quite straightforward. And once they're up at the highest energies that we want them to, they're going around at about 11,000 times per second. And then to bend the protons in a circular path, if you remember your, where do you do this? I guess you do this at A-level physics. To bend a charged particle in a circular path, you need a magnetic field. So we actually have some of the most powerful magnets, at least the huge number of them underground here. We have about 1,200 superconducting magnets. You can see some of them here. They're absolutely fantastic. They're about 35 tons each, about 15 meters long, and actually they're super cooled down using liquid helium because all of them must be superconducting magnets really to get those high magnetic fields that we need. So technology-wise, it's absolutely fantastic what's going on under there. And then at these 4 points here, we have these 4 different experiments. And we collide the proton beams. They sort of come in at the sides here, smash together. Something fantastic happens. All kinds of particles come out. And we've got to try and figure out what happened at that interaction point. So before I get too much into the technology side, this is an absolutely historic experiment that's going on with the Large Hadron Collider at CERN. We've got so many countries around the world, not just physicists coming together, but engineers. We've got accelerator scientists, and now I think a bit more social scientists coming together. Over these 4 different experiments, I'm part of the ATLAS experiment. We've got another general purpose one called CMS, and a couple of specialised ones called ATLAS and LHCb. And we've already achieved most of our physics goals. We've confirmed the Standard Model works. We've discovered the Higgs boson actually quite quickly. We're very pleased with that. But we're still looking for some new evidence of physics and possibly something that's going to produce dark matter or explain dark matter. Now, we share data, we share beam time. This is something that is very different to the rest of physics. When the beams go round the accelerator complex here, they are brought into collision at 4 points at the same time. They cross over at each point. So each experiment is delivered collisions at the same time. And as part of the ATLAS experiment, we all share the data. I don't get 3 days worth of data because I paid for a little bit of it. No, we all share it together. And we all collaborate to try and produce fantastic results. So it's not the same as buying telescope time or anything like that. It really is all shared. It's a very long-term experiment. We turned on in about 2011, discovered the Higgs boson quite quickly in 2012. But this experiment is going to run out to the 2040s at the very least. At the moment, we're sitting here, so we've just finished taking our proton-proton collisions this year. And we're going to probably run next year and in 2026, shift our schedule back a little bit before shutting down, upgrading everything, and then colliding at even higher rates for what we call the high linear LHC. So it's a really, really long-term experiment. Here's just a quick picture of the ATLAS detector. You can see some people here. It is cathedral-sized. It's 5 floors high. And what you have are different layers of specialized detectors that when you put them together and read out the signals from all of them, you can tell one particle from another. You can understand if something's an electron, a photon, a muon, or a spray of protons and neutrons. We can understand that through these specialized layers of detectors. You'll have to take my word from that because we don't have a lot of time. And then one other thing, we take data at such high rates. If you've ever used the cloud to store your photos or any of your other documents, this was first devised by something at CERN because we needed a place to store all of our data, and so we had them spread across the world at different storage sites, and now you have your cloud. But for example, ATLAS, we're getting 40 million collisions every single second. That's a really high rate. But then there's also 100 million readout wires from our detector. That's a huge amount of data to take every second. We can't actually record that. That's too much data to write to disk. So we have to make a decision, and we have a really complex menu of things that we decide then to keep an event or not based on what we've reconstructed. And in less than a second, in about 0.7 seconds, we can decide to write that event to disk, taking those 40 million events per second down to about 2,500. And that has actually only just increased from 300 recently because we've really managed to improve our writing speed from 300 to 2,500 events per second. So that's really cool. We've probably got more now, but about 200 petabytes worth of data, and that's coming on and on as we continue taking data this year. So what are we looking for? Let me tell you about some symmetries. So I'm a big fan of symmetries. There are lots of symmetries in our standard model. And when we don't understand something about our fundamental particles or our forces, we usually find that some arguments of symmetry can help to explain this. This has been so successful in the past. We have discovered the top quark because of this. The W and the Z bosons were discovered under the same principles. The Higgs boson was discovered, and even something simple like antimatter was discovered under the same principles. The positron suddenly turned up after antimatter came about from symmetry arguments. So plugging the hole in our knowledge with the idea of a new particle isn't anything new, and it's incredibly successful. So to try and explain some of the things in our universe, there is a new symmetry that's been theorized between matter particles, which we usually call fermions, and the other particles called bosons. So if you can imagine our universe here with our matter particles, they would actually have a super partner, a shadowy, very massive super partner that perhaps we haven't seen yet. And this is what we call a supersymmetry. It's actually the last one we can do in our universe without breaking everything completely. So there are arguments, for example, for why wouldn't nature have done this symmetry as well as all the other symmetries like translational symmetries and rotational symmetries. But interestingly, it predicts a whole load of new particles. It predicts loads of new particles, which really excites me. So these are all the particles that I showed you before, our 12 matter particles, and then our 4 force particles in our Higgs boson. Now we've got loads. We've got squarks, which are the partners of quarks, and leptons for leptons. And then we've got some particles that are the partners of our force carriers here, like a gluino here, and charginos and neutralinos. And not just one Higgs, now we need 5 for some other reasons. It solves a lot of problems with our standard model that we have. For example, why the Higgs might be so light. But one thing that really grabs me is that the lightest one of these new particles, I'll call them the SUSY particles, supersymmetric particles, this one here is stable, very stable. It's very, very heavy, it's neutral, it's not charged, and it's very, 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 very weakly interacting. It's a fantastic dark matter candidate. So it could have been in the early universe that all of these supersymmetric particles were buzzing around in the same way as the standard model particles were. And as the universe cooled, they froze out and they decayed all down to this one here, which we now see in the form of dark matter. So I find it very exciting and a nice exciting zoo of particles to look for at the LHC. So how do we search for it? Well, with all of these particles, it's really difficult, okay? We have to decide, all right, well, which particles are we going to try and produce? And then how are we going to decay them? What are they going to look like? What kind of experimental signature am I going to try and look for? And so it's very difficult, actually, to look for supersymmetry at the LHC. First, you've got to pin down what you're trying to look for and what it might look like, and then how to separate it or make it stand out above all the standard model physics that's going on in the first place. So what we do in the ATLAS and the CMS experiments as well, we pursue as many paths as possible. We literally look for all of these particles decaying and being produced in all of the different ways that we possibly can. It's a really rich program of searches. We want to leave no stone uncovered. We're not too worried about what the theorists say, as long as we have covered everything experimentally that we possibly can. There's only one LHC. So after all of that, one of the smoking guns, for example, is actually missing energy. If we produce some supersymmetric particles and they do some fancy decay, we know we're going to hopefully be producing our dark matter candidate, which we can't detect. It's completely invisible, but we can infer its presence. So for example, let's say we produce some electrons and some hadrons here. In the transverse plane of the detector, it's just cut away. We would expect expect momentum or energy to be balanced, right? We started off with nothing, it should add up back to 0. But there's something imbalanced here. Something disappeared off in this direction that we didn't detect, missing energy. Now, it could have been something as boring as a neutrino, which actually aren't very boring, but it could have been something that we know about, like a neutrino, or it could be something like dark matter. So what we'd be basically looking for is collecting together all of these events, knowing our standard model might do something like this with a series of simulations, and then looking for an excess. Hopefully our data might agree with something of the addition of these two histograms here. Some nice populated bins of our histograms up there. That's what we're looking for with a lot of our SUSY searches. So where are we at today? So Atlas and CMS are both general purpose detectors. We both saw the Higgs at the same time. We're there to sort of corroborate each other's results and then hopefully also put everything together at the end, but they are two completely independent experiments. In 2015 to 2018, we took about what we call 150, roughly, inverse femtobarns of data. That's sort of our size of our data set, kind of related to the number of events we've collected. And then we kicked off again in 2022, and we've already taken, and I've already done an error, it's not 150, it's 183 by the time we finished the week before last, taking data. So we have a huge amount of data. It's about 66 billion collisions that we have recorded to search through. It's absolutely spectacular, the size of our data sets. You can follow some of the results if you'd like to. I don't know if my slides will be available, but you could always search for Atlas results or CMS results, and everything public you can see there. And we're trying desperately to follow up with the results from this latest run. So here's a snapshot from the summer of some of our SUSY results. And we see no signs of supersymmetry yet. All of these are actually just with the first set of data that we've taken, but we've got more than double to actually go and have a look at. So hopefully we'll see something. But we haven't seen any signs of SUSY yet, and we actually translate that into limits on what could have possibly been there that we can rule out. So if something was quite light, maybe we would have made it abundantly, and we can rule it out based on its production rates and what it would have looked like. It would have produced an excess that we wouldn't have seen. So we can rule out quite a few things. Now, it's difficult probably for some of you to see, but these are the limits on our squarks and our gluinos, and they're produced by the strong force quite abundantly at the LHC if we can access their masses. And they've got some of the highest limits on their masses, but it gets down far, far lower limits on their masses when we get to some of the more rarely produced SUSY particles via the weak force. So there's actually quite a lot in play. Some people do quote these highest mass limits as why SUSY might be dead, but there's a huge amount of things that's still in play that, interestingly, as an experimentalist, are actually much tougher to see experimentally and require quite a lot of creativity in how we can search for the particles. So let's go maybe to some of my favorite ones, which are the electroweak SUSY particles. So producing maybe the dark matter candidate directly, or some of the charged particles that might decay down to it, or maybe some of these leptons. Now, these are some of the least constrained SUSY particles in terms of their masses. If you were producing the SUSY partners of leptons, like electrons and muons, in the best case, they're ruled out up to about 700 GeV in mass by a few things, but there's this very uncovered corridor here, which is very, maybe not alarming, but maybe exciting, that we haven't been able to access yet with our current approaches. It's similar for the chargino and neutralino production. We have these corridors here that are experimentally difficult to access, and we need more data to see them, and we need to get more creative to see them. So these gaps I find very interesting, and a lot of us are throwing a lot of energy into them, not just trying to push these access out to higher and higher masses, but also these great big gaps that are uncovered. So there's a few other ways, and I'll talk about a few other ways as well. Are we starting to smell our dinner before we've opened the door? Where are we sitting at here? Can we see the size of Susie? There's been no fantastic discoveries in excess that I can tell you about today, but there are a few things that we're seeing that might be the first signs of a discovery in the future. One of them is for compressed Susie searches. Let me try and explain these to you. We look for things like a chargino and a neutralino being produced, and they decay to our dark matter particles. Oops, wrong way. And along the way, they can produce a couple of leptons, 2 or 3 leptons here, electrons or muons, that we can reconstruct. So we're looking for 2 or 3 leptons plus lots of missing energy from these escaping neutralinos. Now, interestingly, we saw an excess at Atlas, and we interpreted our results here with the neutralino mass here, and then what the mass difference was between this particle and this particle. Now, interestingly, there was this 2 sigma excess here. This black dotted line is what we expected if we had seen the same number of events that the standard model predicted, but we didn't. We saw more, which left our constraints a little bit weaker. We could only then exclude up to around 140 GeV in mass instead of 180. It made our limits a bit weaker because we saw a 2 sigma excess. So this accounts for our 2 sigma excess. We could not exclude this area here that I'm ringing because we saw an excess. Also what? 2 sigma, 2 standard deviations, that's not much. Let's go to CMS. This is a very similar plot, but a slightly higher production rate because CMS have to do things differently. But their search here also saw a 2 sigma excess and left a very similar area of parameter space uncovered. Now that's really important. It wasn't just seen in one experiment, it was seen in the second independent experiment. Both of the same excess, both 2 standard deviations in the same corners of parameter space. So I'm really, really excited about this. This is something that we could have this trend grow or disappear when we have a look at this set of data that we've just taken recently. So we're throwing a lot of energy at trying to have better sensitivity to these kinds of models because we might have started to see them. Right, and a couple of years ago, LHCb, another experiment round the ring, also saw something very exciting, very, very exciting. They were looking for an extremely rare decay of a B meson, decaying to a kaon here, and releasing a pair of electrons or muons. And the standard model says that it should do electrons and muons at exactly the same rate because the standard model doesn't care if something's an electron or a muon. It treats them exactly the same. It's called lepton universality. So one of our big rules in the standard model. Now, interestingly, this ratio of electrons to muons should have been about 1 here, but that's not what the LHCb experiment saw. In quite a lot of their data, it was far from 1 and actually ended up at about 0.85, about 3 standard deviations away from the 1 that they expected. And 3 standard deviations, it's not quite the gold standard of a 5 standard deviation discovery, but it is clear evidence of something new. And that's sort of saying, oh, get excited, there's something very exciting here. And lots of theorists put out their favorite theory about why this could be, including things like leptoquarks. If you get the theory paper out before the actual discovery, you get the Nobel Prize, you see. So absolute flurry of these papers came out minutes after the result was announced. Very, very strange. So this was very exciting for many years until they updated a few years, just 1 year later, after all the theorists put out their wonderful Nobel Prize winning papers, where a correction was made to the background estimation for the decays to electrons here. It hadn't quite been modeled correctly, and it was having this effect by pulling this ratio away from 1. And in fact, when they remeasured it, it agreed with 1 across the board. So 3 sigma deviations can disappear. That's what I want you to hold in mind. We also have another really fantastic deviation which hasn't disappeared over the course of 20 years. There was an experiment out on Long Island at Brookhaven Lab which measured how the muon's spin precessed around its direction of motion, a bit like a spinning top. And we can use this, basically, this spinning, to really probe very high precision or very, very detailed interactions. So, for example, this spinning top of the muon interacts with a magnetic field by exchanging photons with it. So, for example, muons can just exchange a photon with it, or maybe it can exchange also a photon with itself. We can maybe bring in every other standard model particle that we can think about to start interrupting this, like a Z boson or even a Higgs boson, and make the most complicated diagrams that we can actually think possible, bringing all the known particles of the standard model and make a very, very beautifully precise prediction for what we think the rate of this spin should be. We call it magnetic moment. And we can also build exquisitely precise experiments to match this. So back about 20 years ago, we had this experiment just outside of New York, and we had muons that they're very fleetingly lived, but we can put them in this cyclotron here and store them and measure their spin precession there. And we can measure it to very high precision. And it was quite exciting. The BNL result, the Brookhaven result, didn't agree with the standard model in a very, very, very large way, about just over 4 sigma away, 4 standard deviations away from the standard model prediction. And that stood for 20 years, and a new experiment came along, and it's been built just outside Chicago in Fermilab, which is a bit like the US version of CERN, but less international. And they've measured it, and it agrees with the BNL result. And in fact, you can combine these two results to have an experimental average with very small errors, and it's 4.2 standard deviations away. So this hasn't gone away at all. This could be evidence of something new, maybe something very exciting like supersymmetric muons coming in, and also affecting the way that the muon exchanges photons with the magnetic field here. So I'm very excited here, or it could be a problem with our standard model calculation. Less exciting, but these kind of deviations can stick around. I know, I think I'll have to leave it there because of the time, but I hope I've shown you a little glimpse into what's going on in particle physics, or at least in the high energy particle physics today. I find it a very exciting field to work in, and there's always so much to do. I've been lucky enough to work on the LHC, which is the biggest experiment in human history and will continue to be so for at least the next 20 years as we go on to the high LUMI LHC. We've already found the answer for the Higgs generation, the mass generation with the Higgs boson. I'm hoping that we can move on and find some kind of explanation or step towards the shadowy dark matter in our universe. That would be so much fun. Or even just something completely unexpected that might not be connected to dark matter, but it would be nice if it could be. It is challenging. I mean, to have a look at these kind of very rare signatures, to understand how the standard model might mimic them as well, it's very, very challenging, and we have to dig very deep into the data, all of this data that we're taking, and include it all to try and stand a chance of it. There's also some colliders for the next generation that I didn't have time to say anything about, but there's definitely some more digging through data on the horizon, be it the high LUMI LHC or maybe its next generation. Thank you.